Okay, today we have a speaker, Professor Vladimir Dotsenko. He is from Strasbourg, France, and his talk is Old and New Aspects of the Poincaré-Birkhoff-Witt theorem. Please.
Thank you very much. I am very happy to give a talk here. So it will be mostly about joint work with Pedro Tamaroff, who did his PhD with me and now is a postdoc in Berlin. It's published in IRMA 2 years ago, and somehow, yeah. So it's not a very new result. It was proved several years ago, but somehow I think that it is a good topic to discuss for the following reason. So somehow it's an example of how some ideas from category theory can be applied to questions about varieties of algebras. And I find that somehow nowadays we're finding more and more situations like that. And so it's something I would like to share with you. Perhaps it's some of the methods related to the methods I will talk about might be useful in your work. As the title says, I am going to talk about Poincaré-Birkhoff-Witt theorems. So the classical Poincaré-Birkhoff-Witt theorem concerns universal enveloping algebras of Lie algebras. And somehow, well, we all know that Lie algebras are form a very remarkable non-associative structure. And in particular, as far as universal enveloping algebras are concerned, there is some truly remarkable coincidence that happens. So when we talk about universal enveloping algebras of Lie algebras, they exhibit a remarkable coincidence. Namely, there are two a priori different definitions that happen to be equivalent. So one definition is that given a Lie algebra L, the universal envelope U of L is an associative algebra whose left modules are the same as representations of L. Representations of L. The second definition, which is a priori different, realizes the universal enveloping algebra as a, well, categorically one may say as a left adjoint to the forgetful functor from associative to Lie algebra. So what I mean is the following. So for each associative algebra, A, one can define a Lie algebra, often denoted A minus. So one can define Lie algebra A minus, which is the same vector space with the Lie bracket given by the commutator AB minus BA. This construction, it agrees with morphisms of associative algebra. So it defines a functor. So it is a from associative algebras to Lie algebras. And this functor admits a left adjoint. So there is this minus functor like this, and there is the adjoint functor, the inverse enveloping algebra, which means that you take a Lie algebra and you informally, yes, you kind of generate out of it the associative algebra, assuming that in that associative algebra, you have the bracket of AB equal to AB minus BA. So the inverse enveloping algebra of a Lie algebra is the left adjoint of this functor. And the Poincaré-Birkhoff-Witt theorem concerns, says something about this, so says something about this inverse enveloping algebra. And so in a sense, well, we will see. So for in some moments, you will see that I am going to primarily focus on the second definition, or the second interpretation of the inverse enveloping algebra, and the first interpretation I will only address towards the very end of the talk. So what does the Poincaré-Birkhoff-Witt theorem say? Let me change the page. So there are sort of several different versions of this theorem, but they all say that in some sense, the inverse enveloping algebra of Lie algebra L looks kind of similar to the symmetric algebra of L. So the S of L. So what can it possibly mean? One possibility is to say that there is a vector space isomorphism between these two vector spaces, which, if you state it like that, it's a ridiculously weak theorem, right? Because both U of L and S of L are, if we work over a field, are vector spaces of countable dimension over the ground field. So yeah, they are isomorphic. It's not terribly deep. The second option, which sometimes is used in representation theoretic context, says that both of these guys can be equipped with the adjoint action of the Lie algebra. So the adjoint action of the Lie algebra on itself extends in an obvious way to U of L and S of L. And so if we equip these vector spaces with the Lie algebra action, they are isomorphic as L modules. With action arising from the adjoint action. This is all a little bit more, but still it's a little bit, it's not perhaps not too much still, because, well, yeah. Then there is another way in which these things look similar. It turns out that the universal enveloping algebra of any Lie algebra happens to be a bi-algebra, even a Hopf algebra. And so if we want to look at the co-algebra structure on U of L and the obvious co-frequent nilpotent co-algebra structure on S of L, then these two are isomorphic. So, so another possibility is that isomorphic as co-algebras. And well, you can also say that U of L is a deformation of S of L. Namely, you can take S of L, which is after all just polynomials, define on it a Poisson bracket arising from the Lie bracket of L, and deform S of L in the direction of that Poisson bracket. And you get, it turns out that you can deform, and the result is U of L. So, and there are sort of many, there are some other possibilities of what you can say. And somehow, so as I said, the first two statements are, if you state them like that, are a little bit weak. So you can improve them a little bit, so you can actually exhibit compatible bases using Grobner basis and diamond lemma. But yeah, so you can say more, but if you state it like that, it's definitely not enough. If we talk about coalgebras, that's much stronger and nice in many ways, but you use some extrinsic structure, which is means that if you want to generalize this theorem to some other situations, maybe you won't be so lucky and there will be no such extrinsic structure. As for, yeah, deformation, yes, so this uses very much the fact that you can deform things in the direction of Poisson brackets. So it's also a little bit specific for this particular case. So a little bit hard to generalize, I would say. What I'm going to explain in this talk is another way to view this theorem, which somehow takes exactly what is needed. So if you think about the universal enveloping algebra as the left adjoint of the forgetful functor, somehow the statement that I'm going to make will literally use just that. But to give that statement and to explain to you this framework in which you can actually generalize the Poincaré-Birkhoff-Witt theorem in very meaningful ways to other algebraic structures, I will need to talk a little bit about the language of category theory that I am going to rely on. So some category theory. So, okay, so we start with, when of course, I am assuming that we all agree that to define a category, we normally would define objects and morphisms. And in our case today, I suggest to think of the following examples of categories. The category of vector spaces over some field where morphisms are linear maps. So vector spaces. Objects are vector spaces, and the category of some type of algebras of a certain, for a certain variety V, where objects are algebras themselves and morphisms are homomorphisms of algebras. So maps that respect the structure operations. Now, once you start thinking about categories, you can also start thinking about functors between categories. And a functor between two categories, it's a way to produce from an object in C an object from D, so that this way you construct objects is canonical, so it respects maps, morphisms in the category C. So a functor is a recipe constructing objects in D from objects in C that respects morphisms in C. Meaning that whenever you have a morphism between two objects in C, you have a morphism from the corresponding constructed objects in D, which compose in the same way as morphisms, the original morphisms in C. So, for example, this construction from A that goes from A to A minus, as I said, is a functor from the category of associative algebras to the category of Lie algebras. Okay, now the most the next thing that we're going to need is that among functors, if the source and the target are the same, we can talk about end functors. So an end functor of a category C is a functor from C to C. And so you should think of it as some kind of higher level generalization of an endomorphism of an a vector space, so for example. And endomorphisms of vector spaces you can compose with each other, and the functors you can also compose. So if you have f from C to C and G from C to C to n the functors, then you can compose GF is an end functor from C to C, which, well, each functor is a recipe of how to construct objects. So you first construct a new object using the end functor F, and then apply the end functor G. We will see some examples in a moment, but before that, let me remark that composition of end functors is of course associative, the same way as composition of endomorphisms or composition of functions. G, F, H is the same as G, F, H. And because of that, we can do something which is quite natural if you spend some time doing category theory, might look a little bit bizarre. Otherwise, we can look at end functors which are monoids. That happen to be monoids. What does it mean? A monoid is in a monoid we can compute products. So in terms of an end functor which is a monoid, it's an end functor F such that if you apply, so you can compute the composition, you apply F twice, and you have a natural transformation of between F applied twice and F. So natural transformation. Meaning that for every object X, we have maps, we have a map from f of X to f of X. From F composed twice to F, and these maps are compatible with morphisms in C. Well, this is a product, and we also require unitality. So there is, so we want this product, which is associative, meaning that if you, so you have the composition of F 3 times, you can compute the 2 different compositions to F 2 times, and then finally product. And these should be the same. And you also require this product to be unital. So there is the identity and the functor. I, for any category C, there is the identity and the functor that sends any object X to the same object X. and also the same with each morphism to the same morphism. And we want a natural transformation, of and the functors from I to F satisfying unitality property. What I mean is the following. So I mean, this might look terribly abstract, and in a moment I will try to explain how to think about all of that. But so informally, if you have so a usual monoid M, it's a set with a binary operation and unit such, so the binary operation, so it's from M times M to M. Unit you can view as somehow the inclusion of element of a set consisting of just the unit of one element into M. And this should satisfy some properties which you can express as some commutative diagrams. And then if you replace the product by composition of n defunctors, then you get precisely the conditions that you want to hold for n defunctors. And an n defunctor like that, so an n defunctor that happens to be a monoid, those are so monoid n defunctors are called monads. Okay, so let me give you a couple of examples, because this has been terribly abstract, but now let me give you a couple of examples that hopefully will clarify things a little. So from now on, in the following examples, the category C is going to be the category of vector spaces. So the first example is as follows: let V be a vector space. We fix some vector space. Then we can define an n defunctor of C. Of the category of vector spaces. By putting F of a vector space W equal to V tensor W. So this is a very easily seen to be a functor. So if you have a map from W1 to W2, of course, you have obvious map from V tensor W1 to V tensor W2. So this construction is compatible with morphisms of vector spaces. And somehow this, so making this n defunctor into a monad is equivalent to making V an associative algebra, a unital associative algebra. Why is it the case? So we want the product a natural transformation from FF into F. So this is the same as maps from V tensor V tensor W into V tensor W for all W. In particular, for W equal to the ground field, we want such a map. So we obtain, we get map from V tensor V into V, so a binary operation on V. And this binary operation is going to be associative because of the associativity on the level of n the functors. And now we want, so the a natural transformation from the identity and the functor into F. So this means that we want maps from W to V tensor W for all W. Again, if we put W equal to the ground field, this is a map from the, from the ground field, a linear map from the ground field into V, which is defined by the image of the unit element of the ground field. So this is a specified vector. In V. And the unitality property guarantees that this vector is the identity for our associative product. Unit for the associative product. So, well, for the moment, this example is a little bit, well, it's not perhaps very convincing to you because this is a very, very, very strange and abstract way to talk about associative algebras that we all know and like. Let me give you another example. So the second example. So I'm still working with the category of vector spaces. And now let me define an the functor F that
excuse me, can I ask you about your previous example?
Yes, of course.
Yes. Thank you very much for your interesting talk. But when we make your endofunctor into monad, what is the unit of this monad?
So
this is
making endofunctor into a monad means that we want to define a product and we want to define a natural transformation from the identity and the functor, right? So I am saying that defining a natural transformation from the identity and the functor, if we evaluate it on the ground field, we get a specified vector in V, and then for any vector, for any W, a map from W into V tensor W. So if you call this specified vector 1, then this map will send every vector W into 1 tensor W. So once you, so the logic is here. The logic is like that if you have a natural transformation from the identity and the functor, you can in particular specify it on compute it on the ground field, and this way you get specified vector, and then somehow you can figure out that it immediately gives you a a map from natural map from W to V tensor W for any vector space W.
Thank you. Thank you. I
All right.
understand.
Thank you very much. So now let me define an end functor which doesn't depend on any choices. Let me assign to a vector space W the space of all tensors on W. So it's ground field plus W plus W tensor square and so on. So this, you start from a vector space W, you get the space of all, the direct sum of all tensor powers. So it's a much bigger vector space, an infinite dimensional vector space, but still a vector space. And of course, it's a functor. Any map from W1 to W2 induces a map from tensors on W1 to tensors on W2. So, and let me explain to you why this end functor is a monad, because this will be of very important for us in a couple of minutes. So this end functor is a monad. The argument is as follows. So we need to obtain a natural transformation from F applied twice to F, and a map, a natural transformation from the identity and the functor to F. So we want to apply the tensor monad twice and have a map to the tensor monad. And we want to have a map from W to T of W. And we want these to satisfy the associativity and unitality condition. First of all, the map from W to T of W, it's the obvious inclusion. W is a direct summand of T of W, so such a map we definitely have. That's perfectly fine. How to construct a map from T of W into T of W? Well, T of W, it's a huge vector space. So you take a tensor algebra of an infinite dimensional vector space. So yeah, but how to have a map like this? So elements of T of W, these are kind of tensors of tensors. So you have expressions like W1 tensor W2, tensor W3, tensor W4, tensor W5. So this is in W tensor square, this is in W tensor cube, and so the tensor product of W tensor square, tensor W tensor cube, you view as inside of T of W. So that's so this is a typical element of this double tensor space. And of course, there is an obvious map from here to T of W. You can just erase all these brackets. You can view this element directly as a tensor in W to the tensor power 5. So this is forgetting the nesting of tensors. And somehow it's a very easy exercise, which I'm not going to do for you right now, that this structure, so this product on F and the natural transformation from the identity and the functor, they satisfy associativity and unitality. This example can be easily generalized. So let V be a variety of linear algebras. So some variety of algebras in the category of vector spaces. So associative algebras, Lie algebras, any kind of algebras you might want to think of. Then we can consider an functor that sends W to the free algebra in this variety generated by W. And they claim that this is also a monad. And the tensor monad before, this was just, so this previous example corresponds to the variety of unital associative algebras. Because if you take the tensor, the space of tensors, this is indeed the free unital associative algebra generated by W. And the monad structure is as before. So the maps from W to free algebra generated by W is the inclusion of generators. And the map from the free algebra on the free algebra of W into the free algebra on W is forgetting the nested structure of elements of free algebras. Why? So this is absolutely crucial. So why is this important for us? So we can define, so suppose now, so let F be a monad on C. Then we can define algebras over F. An algebra over F is an object X of C. And the structure map from F of X into X that satisfies the following conditions. You can compute F of X, which is the same as F applied twice on X. And you can do you can compute, you can do two different things. You can go from here to F of X because F is a monad, or you can go to F of X because there is a map from F of X to X, the structure, and you use the fact that F is a functor. And then you can apply, you can go, well, let me do it later. You can go to F of X because F is a functor. So here we use monad on F. Here we use the structure on X. And then you can use the structure on X, and the results should be the same. And you also would like to use the unitality condition. So you have an natural transformation from I to F, and then you can apply the structure map to X, and I of X is the same as X, so this diagram should commute. And the main property, so, well, not the main, well, let me just summarize. Let me state what happens in the examples that we considered. So in example 1, if V is an associative algebra and W is an algebra for the monad of tensoring with V, an algebra is the same as a left V module in the usual sense. So an algebra for the monad of tensoring is a module of the left module of the corresponding associative algebra. In example 2, an algebra over the tensor monad is a unital associative algebra. So what does it mean? So you have W and the structure map from T of W into W. Then, of course, you have, so T of W, it's ground field plus W tensor square plus W tensor cube and so on. So you have a map from K into W. So you have a specified vector. You have a map from W into W, but this should be the identity because of compatibility with the unit. You have W tensor square into W. You have a binary operation. And then I claim that the associativity means that all the higher maps from W tensor cube and so on, they are just iterations of the binary product. And the specified element is the unit for the binary product. So that's a little exercise that I'm not going to do. And similarly, algebras for the monad of the free algebra are algebras of the variety V. So somehow this is a categorical way to talk about varieties of algebras. Now let us go back to what we started about the functor, the minus functor from the associative algebras to Lie algebras. This is a functor, so so I should have said perhaps, well, now it's a good moment to say that. So in general, questions, natural questions about these functors like that and their left adjoints were systematically studied by Mikhailov and Shostakov in their paper PBW pairs of varieties of linear algebras. So they said that sometimes between some varieties of algebras, you have a functor of change of multiplication, similar to this minus functor that creates a bracket by the formula AB minus BA. Or for associative algebras, you can think about the plus functor. So AB plus BA, and this way you get special Jordan algebras. And there are many other situations like that. And then somehow so Mikhailov and Shostakov defined the PBW property in a certain way. So they say that so PBW is that the left adjoint functor can be described without using the multiplication in the algebra. So we can describe the underlying vector space of the universal enveloping algebra in this as the space of symmetric tensors. That's what I was studying. So let me explain a little variation of this, explain how to use monads to reformulate it in a precise categorical way and then use it. So suppose that we have P and Q are two monads now, and we have natural transformation of monads from P to Q. Natural transformation of monads, meaning that it's a natural transformation of functors that respects the monad structure. So this means that for every W, we have, or maybe let me say, well, yeah, for every W, we have a map from P of W into Q of W that is respects the monad structure and respects morphisms between different W's. Of course, if W is a Q algebra, that is, we have the structure map from Q of W into W, then this gives a map from P of W into W. We can take Q of W to W and compose it with the map from P of W to Q of W. So this gives an algebra structure, a P algebra structure on W. So somehow a natural transformation of monads can be used, a natural transformation from P to Q can be used to create from Q algebra structures, P algebra structures on the same vector space. And this is what is natural to call a functor of change of multiplication. Let me say, yeah, so phi, let me denote this map, transformation of monads, phi upper star from Q algebras to P algebras. And then, so under some assumptions and on P and Q, there is, and the category C, there is a left adjoint functor phi shriek from P algebras to Q algebras. And this is the reasonable to call the universal enveloping algebra. just as a remark, so the functor from the associative algebras to Lie algebras, the minus functor, it's an example of the following thing, of that same thing. So if we take the monad of the free Lie algebra and the monad of the free associative algebra, there is a transformation like that. So there is for every V, there is a map from the Lie algebra, from the free Lie algebra into the tensor algebra, which is the usual embedding of the free algebra in the tensor algebra. And this gives you a morphism of monads from the Lie monad to the associative monad. And this is precisely corresponds to the minus function. Now, so the PBW property, says that the underlying object of the universal enveloping algebra, phi shriek of X, can be computed as A of X for some n functor A, and the isomorphism phi shriek X with A of X is natural with respect to P algebra maps. So in the classical case, the universal enveloping algebra as a vector space is isomorphic to the space of symmetric tensors, which is also an n functor of the category of vector spaces. And so we require naturality with respect to Lie algebra morphisms. Now, let me conclude with stating the main theorem. Let P phi from P to Q be a natural transformation of monads. The PBW property for universal enveloping holds if and only if Q is a free right module, free right P module. What does this mean? I was telling you that monads are monoids, where with the product given by composition of n functors. If you have a map of monoids from M to N, then of course N becomes a module over M on the left and on the right. You can map M into N and multiply there. Similarly, if you have a natural transformation of monads, Q becomes a module over P on the left and on the right. And a free right P module means that it's a P module of the form let me some letter Y P, where Y is some n functor. So with free P module freely generated by some n functor. Now, let me just take 2 minutes. So to say the following. First of all, this theorem, its proof is almost trivial. So it's in some sense it's a matter of choosing a good definition. The theorem in this way is not very difficult to prove. why is it useful? Because there are some techniques coming from operad theory, techniques that allow us to test this condition of being a free write module. So somehow techniques that allow actually to do some little calculation and verify. In examples of main interest to us, in examples that I mentioned before, where you have a monad of, all monads are monads of free algebras for certain varieties of algebras, and phi is a functor of change of multiplication. Somehow, so in particular, we were motivated originally by a question asked by Jean-Louis Ladey. So there is a variety of algebras called dendriform algebras, and a much more famous variety of algebras called the Prelli or right symmetric algebras. For Prelli algebras, the axioms say that the associator is symmetric in the last two arguments, and dendriform, it's a slightly more complicated, so it's some way to split associativity into two parts. And Ladey asked, so there is a morphism of monads of the free Prelli algebra into the free dendriform algebra. So there is a functor of change multiplication that makes every dendriform algebra a Prelli algebra. They asked if there is a PBW theorem for the for the inverse enveloping algebras, and it remained an open question for a while. We proved it. So then there was an independent proof by appeared by Vsevolod Gubarev. So it's possible to do it not using monads and operads, but well, using monads and operads give you some extra bit of functoriality that sometimes is useful for some purposes. Okay, so I think that I took enough of your attention, so I will stop here and thank you for your patience.
Okay, thank you very much. Are there some questions or comments?
Sorry?
May I ask you a question?
Yes.
What does it mean that theorem in the language of Lie algebras, or Lie algebras, what does it mean?
Sorry, say it again.
Theorem you formulated here.
Yes,
In the
right.
language of Lie algebras, or Lie algebras, what does it mean?
Yes, great question. So for Lie algebras, so there is a as I said before, there is a map from the Lie monad to the tensor monad, and the tensor monad is free as a right Lie module, so it's free under Lie substitutions. And this means, so this freeness property, it's actually the PBW theorem for free Lie algebras. It says that the free associative algebra is isomorphic to the symmetric algebra on the free Lie algebra. So somehow the theorem morally says that to prove the PBW theorem for Lie algebras, it's enough to prove it only for free algebras.
Are there some other questions or comments?
Excuse me, TV is an associative, free associative algebra. S is the commutative algebra. How can they be isomorphic here?
No. This is an isomorphism of vector spaces.
Okay, thanks.
excuse me, and how translates in this framework when we have the PBV is decomposed into plus part, minus part, Cartan part?
Oh, is this in some sense PBV? No, I mean the decomposition of a semi-simple Lie algebra into two nilpotents and Cartan. It's I mean I don't tend to think about it as PBW. It's some particular thing that you can do for some particular Lie algebras, whereas for me, PBW type theorems, they concern some situations like that of universal developing algebras, that something that you can do for all Lie algebras, no matter what.
You mean that the other what I asked was only for semi-simple case,
Right.
and your construction is more general.
Yes.
Okay.
Yes.
Okay.
Some other questions? If no more questions, we close the official part of the seminar. Now you can speak in any language which is